So that leads me to introduce the second speaker of this session, which is Arnold Kell from ICI. So Arnold has a BSc and a PhD in chemistry and 15 years of R&D experience at the National Research Council of Canada. Sorry, wrong one. That's right. And yeah, working on nanomaterials for biodiagnostic applications. He's currently the technical leader of molecular silver ink activities for printable electronic applications. And he's focusing on transistors, RF circuits, and antennas. And in addition, recent efforts have been focused on the development of inks that can be utilized in stretchable and structural and in-mold electronics. So a huge variety of technical topics there. I look forward to hearing about them, as I'm sure does everybody else. Over to you, Arnold.
Okay, thank you. I assume everyone can hear me?
Yeah, no problem at all.
Okay, perfect. Okay, so I would like to begin by thanking Michelle, Howard, Chloe, Helen, and the rest of the people at ICI for the opportunity to speak today. It's always really nice to connect with the PE community, and I hope you enjoy my talk. If we can go to the next slide, please, Chloe. So for those of you that are not familiar with National Research Council, we are Canada's largest federal research and development organization. We really strive for research excellence, and we try to have impact through knowledge advancements, the development and creation of new technologies, as well as taking opportunities to work with really innovative and creative partners in order to have a positive impact or influence on Canada's economy, the environment, as well as society as a whole. So the work I'm going to talk about today has been carried out at the Security and, go back one, Chloe, the Security and Disruptive Technologies Research Center in Ottawa, as well as the Automotive and Surface Transportation Research Center in Boucherville, Quebec. And the focus of the NRC effort within the scope of this presentation really is the development of advanced materials and the engineering of advanced materials. We can go to the next slide. So we've had the privilege of working with a really innovative partner in E2IP Technologies. This company is headquartered in Saint Laurent, Quebec, and they're global leaders in the design, engineering, and manufacture of human-machine interface technologies. They take a really unique approach to the design of these HMIs, where they have a real marriage of design and advanced materials, and this has let them really innovate the space and sort of reimagine the way that we can interact with the objects in the world around us through touch interfaces. We can go to the next slide, please. And so what's really the thread that's really drawn NRC and E2IP together is the development of these molecular ink platforms that can be incorporated into scalable printing processes in order to create all printed devices with enhanced or even entirely new design criteria or properties. And the presentation today is going to focus largely on some unique processing capabilities that we have with these inks, some UV processing, some unique material properties of these inks, specifically elongation during thermoforming, and how those things can let our team really innovate the HMI space. Can we go to the next slide? So molecular inks are particle-free. They're usually composed of a silver precursor or a silver salt that's dispersed in the ink, and you can trigger the formation of a conductive film by exposing the traces to either heat or light. We've developed a new formulation of molecular ink that actually allows us to do this with UV light, so either broadband or UV. And the mechanism by which this happens is we initially have a photo reduction of the silver salt, and that initiates the formation of some silver nanoparticle. The nanoparticles then absorb light, and that sort of heats the entire system up. So you rely on this absorption of light, heat generated by the nanoparticles, and that pushes the decomposition of the rest of the silver salt in that trace into other nanoparticles. Because you're at a high temperature, the stabilizing ligands and the solvent evaporates, and you're left with a relatively coalesced, pretty conductive film. So we get sheet resistivities under 5 milliohm per square per mil. This process is pretty fast, about 4 times faster than the comparable traditional process carried out in an oven. And it's interesting because this heating process I described is self-limited, so it really only keeps heating up as long as nanoparticles are present. When the trace becomes silver and reflective, the temperature plateaus, so you don't damage the substrate. So we were really intrigued by the control that we could exert over this reaction. And it got us thinking perhaps we might be able to use some of these interesting molecular inks and our ability to control the chemistry to actually produce some three-dimensional electronics. And if you can go to the next slide. So one avenue to allow us to do that is through a thermoforming application. So you can imagine if we have this ink, it's printed on a substrate, we can put that under an overhead oven. In this case, the substrate is polycarbonate. If you heat the polycarbonate up to the point that it softens, you can pull it down onto a vacuum table that has a mold on it. So this mold would be coming up out of the table. As you pull that softened substrate onto the vacuum table, it will pull the softened substrate all around that mold. And you basically transfer whatever mold you have into the plastic, and it freezes there as a substrate cools. So this is an interesting way of creating a 3D electronic. It's quite simple, but the challenge is that when you transition from 2 dimensions to 3 dimensions, the substrate elongates, which means the ink elongates. So the formation of these three-dimensional, oh, you can go back one, Chloe, please. So the challenge in creating these types of electronics is, or really hinges on the ability for the ink to elongate and having the ability to minimize the change in resistance. So if you can go to the next slide. So with respect to molecular inks and the molecular ink in particular that I'm describing here, it turns out that if you simply print that and carry it through the thermoforming process, it will crack and become non-conductive. However, if you expose it to UV light and or a window of UV light that I refer to as a UV treatment, and you stop short of completely converting it into a conductive silver film, it turns out that you can take those UV treated traces, put them in a thermoformer, heat the substrate up until it softens, pull it down over top of a three-dimensional mold. So in this case, again, the mold is sticking up out of the trace or out of the vacuum table. You can pull that down and you get traces that don't crack. So this was pretty interesting. And if you go to the next slide. With a collaborator that we have, another NRC collaborator, Hiroshi Fukutani, was able to design a circuit, and we could have a circuit that had a height of about 1 centimeter. The traces undergo an elongation of about 18% without cracking. We could have a nice little touch sensor where we could activate 3 LEDs. It's run by an Arduino board. And the volume resistivity of these inks, even when they're thermoformed, are about 5 times lower than the commercially available inks. So this was a really nice result, and it was a really great start, and it got us thinking we could probably incorporate these inks into thermoforming and eventually IME applications. But if you go to the next slide, in order to do this, there are a lot of requirements that industry is going to have that we're going to have to test if we can meet. So one of the first requirements is that rather than printing on a bare substrate, you're going to have to print on what's referred to as an ink stack. So this is typically a series of graphic inks and dielectric inks. And the reason that you want those is because the device, first and foremost, has to be aesthetically pleasing. It has to look nice if you're going to install it somewhere. Secondly, it has to give you some indication of what it does. So you're going to have some LEDs on it that indicate what function it has and what the device is going to do. Secondly, the circuits in the previous case were printed directly on top of the substrate, and we were accessing them by touching the printed circuit. That's not going to be what you use in real life. So the circuits are going to have to be printed on the inside of the device, and you'll have to access them through the substrate. So this means you need an entirely new type of thermoforming. Specifically, rather than having the mold sitting on top of the vacuum table, you're going to have the mold going into the vacuum table. And typically, this type of thermoforming requires a lot more elongation. So some unmet needs, if you're going to do something like this, is the development of inks that have really good electrical properties, in particular if you're elongating to 50% or even greater. So our colleagues at AST, Paul Trudeau, produced these progressive cone structures. So this is the vacuum table that I'm showing in the middle. And it's sort of deceptive. It's like an optical illusion, but the image on the right-hand side, those traces are actually going into the screen from you. And what this is a series of molecular ink traces printed on graphic or on an ink stack. And from the right-hand side, there's 0 elongation. As you go into the cone, you have a depth of about 0.5 centimeters and an elongation of around 5%. And as you get to the left side of the cone, the elongation there is around 40% or 40 to 47%. And the elongation, and the depth is around 4.5 centimeters. So if we go to the next slide. So it turned out that in comparison to a lot of competitor inks that are used for thermoforming applications, the molecular inks for line widths of 250 to 1,000 micrometers wide perform pretty well. So the initial resistance that you measure across those traces is as low or lower than most of the competitive inks. As you move to the right hand, or as you move right across each of these plots, you'll see that the resistance changes less as the elongation increases. And if you look further to the left, around 40, or to the right, excuse me, around 43% elongation, most of the traces break by 38 to 43% elongation, whereas the molecular ink traces remain conductive at that point. So if we go to the next slide. So this was interesting from the perspective that that we thought it might be interesting to try to make a first generation device that took advantage of the fact that our inks can be elongated further than other inks are capable of being thermoformed in order to show that such a device could be made. And perhaps this is going to lead to some imaginative devices and a push forward in the impact of these types of devices. So what we've shown here is the sort of the structure of the architecture of the device that I'm going to show in the next slide. Again, you can see the flake inks that are on the top right. Sorry, can you go back one slide, Chloe? So the inks on the top right crack, and the molecular inks that are on the lower right have not cracked. Okay, so the next slide. So this just takes you through the creation of our first generation in mold part. So from the top view, you can see we've got some indicators, a logo. And from the bottom side, we have the ink stack. So we printed a graphic ink, or a series of graphic inks. We printed a dielectric and the molecular ink. We then thermoform it and place the electrode, or place some LEDs inside the device. It might be a little bit hard to see, but you can even see that all of the buttons have also elongated in both the X and Y direction about 50% during this thermoforming application, as well as the traces coming up the side. And in the final step, we have to mold and encapsulate the part in order to rigidify it. So if you think of like your dishwasher or a coffee maker, the molding and rigidification process would basically let you install this part into something by clipping it in, and it would have a nice hard shell. If we go to the next slide. So again, this injection molding process is carried out at AST. It basically involves nesting the thermoform part into a mold. You then take basically a plug structure that's slightly smaller than the thermoformed object. You pin those together, and that's shown. So the device, or the two halves of the injection molding tool, are shown in the middle. It sealed together is shown on the far right-hand side. And you then inject high pressure molten polymer, high pressure, high temperature molten polymer into this. And if you go to the next slide, you can see that you've put a hard coating of polymer on the underside of this circuit, encapsulating, or on top of this device, encapsulating the circuit and the LEDs. And in the left-hand side, you can see that one of the LEDs is lit up. And so this could be a device. There's a front view and a back view of this device. It's a little bit difficult to see, but essentially you have some buttons there that you can activate, a slider. You have a logo, and you could hook this up to, for example, an Arduino board and run it. Again, I want to stress it's got 50% elongation, both at the center of this device and with the tail coming out, and about 5 LEDs are inside of it. We can go to the next slide. So we were able to achieve 50% elongation, but we wondered how far we could actually push this. So you can see here, using a biaxial stretcher, we can take these elongations to around 100%, and the traces remain conductive. And this was really sort of groundbreaking, and it got the designers at E2IP quite excited. So if you go to the next slide. And it really opened up many opportunities for the designers at E2IP to really dream about the types of HMI devices they could create. So this process essentially culminated in the development of the avatar that we're showing on the right-hand side of the upper right-hand side of this slide, which is a prototype device that's proposed to act as a user interface and control interface for seating in the first-class cabin of airliners. So what's really interesting about this device, and what allows it to only be made using molecular ink, is that around the knob feature, just underneath of the lock there, all of the traces have been elongated about 100% in that area. and the only ink that can really achieve this is ours. So this was innovative enough to be considered as one of the 3 finalists for the 2020 Aircraft Interior Expo Crystal Cabin Award. Unfortunately, because of COVID, no award winners were announced last year, but I believe we have a newer generation of it that we're going to be resubmitting this year, and we'll be hoping for the best with respect to that. So to summarize, our team has really created an ecosystem of innovation, and we kind of see ourselves moving towards being a one-stop shop of expertise, where we've got device and circuit designers, ink developers and printers, as well as materials chemists working on thermoforming and unique molding techniques that really allow us to reimagine how HMIs can be designed and reimagine how we can interact with the world around us. If we can go to the next slide. I just wanted to touch on one thing before I leave. We have a booth. I would love to talk to more people about this, but we've also developed some really unique ways to produce conductive 3D printed parts, again, using molecular inks and a combination of SLA printing, where we can control where the molecular ink goes to during the polymerization process. You can then post-thermally sinter these things, and you can get really unique strain sensors based on matrices, and we've even been able to make some antennas. And if you would like to learn more about that, there's you can come to our booth, give me an email, or I can put you in touch with Chantal Paquette, or you could read this paper in Nature Communications. If we can go to the next slide. Okay, so this is it. This is the team. Super proud to be a part of this team. We've got a lot of really great people working hard, materials chemists at SDT that have co-developed the ink with researchers at EYP, some really great materials chemists and materials engineers, or sorry, I should say materials engineers at AST, circuit designers from AEP. And this has also really been driven, and I don't want to leave out the business people that have really pointed us in the right direction and sort of helped us learn that we've got something really unique and kept us on track. So with that said, I thank you for your attention, and I will sign off.